Hi, welcome to Pathways to Chemistry. This is Dr. O'Connor. In this video, we're going to talk about molecular shapes, and we're going to determine molecular shapes using the valence shell electron pair repulsion model. We're only going to do a few different shapes here. Linear, we'll do trigonal, planar, and tetrahedral. And of course, with tetrahedral, we have trigonal, pyramidal, and bent. So those are the only ones we're going to do. The octahedral and others will be for a different course. Okay, let's go ahead and start out with some of the structures that we drew previously. So remember, first, in order to determine a molecular shape or an electron pair geometry, the first thing that you need to do is draw the Lewis structure, but we've already covered that in another video. So let's take a look at methane, and we know that the Lewis structure for methane is this one here. And if you remember in a previous video, I called the bonds and any lone pairs of electrons charge clouds. Okay, so what we're interested in is the central atom, in this case the carbon. So here I see the carbon has 4 charge clouds, if you will. So 4 charge clouds, and how many lone pairs on the carbon? 0 lone pairs. And how many bonds? All 4 of the charge clouds are the bonded atoms because we have no lone pairs. So when we have a situation like this, where we have 4 charge clouds, 0 lone pairs, about a central atom, then this is called a tetrahedral electron pair geometry. Now, as far as the molecular shape goes, in this case here, the molecular shape, or structure as your book calls it, is the same as the electron pair geometry. And that's because we don't have any lone pairs. So here, our molecular geometry, or molecular shape, is also tetrahedral. Okay, let's take a look at another one. And let's look at ammonia. And we know that ammonia has this Lewis structure. So we have the 3 hydrogens and the lone pair of electrons. So obviously we have 4 charge clouds, the 3 bonds and the lone pairs of electrons. So, or I should say lone pair of electrons, that's 4 charge clouds. But we have 1 lone pair on the nitrogen, and of course 3 bonds. Now, because it's 4 charge clouds, the electron pair geometry is tetrahedral. But because of that lone pair of electrons, the molecular geometry, I'll just abbreviate that Mg, or molecular shape, is not tetrahedral. Remember, we have this lone pair of electrons under the influence of only the 1 nucleus, where the bonding electrons are under the influence of 2 nuclei. So these tend to strongly repel the bonding electrons, and therefore that will decrease these bond angles. So it compresses, because of the lone pair, we have compression of the rest of the molecule. So the molecular geometry is not the same as the electron pair geometry. So in this case, for ammonia, it's trigonal pyramidal. So trigonal pyramidal. Okay, so that's for ammonia. Now let's take a look at water, and we can draw the Lewis structure for water. And what we have is something like this. Sorry, my drawings are not great. Remember, we have the 2 lone pairs on the water. Now, again, here we have the 4 charge clouds, 2 lone pairs, and 2 bonds. Okay, so now we have these two lone pairs of electrons, and again we have a tetrahedral electron pair geometry, and we have a, let me finish writing this out. As far as the molecular geometry goes, we have these two lone pairs. And remember what I said, those lone pairs are going to strongly repel these bonding electrons. This compresses the angle even more. Okay, so there's no way that the molecular shape is tetrahedral. In fact, the molecular shape or molecular geometry is bent. So next, we'll take a look at this phosphorus trichloride. Let me just move this up a bit. And so we can draw the Lewis structure for phosphorus trichloride. We did this in the previous video. Go ahead and put my electrons about the chlorines. And let's see, we have one electron pair on the phosphorus. So again, here we have 4 charge clouds. So we have 3 bonds, and there's one lone pair on the phosphorus. So one lone pair. So in this case, what we have is we have a tetrahedral electron pair geometry, but the molecular shape is trigonal planar. Let's take a look at these two here. Remember that pair of isomers that we had before. So we'll do this one. So this is the dimethyl ether. Okay. Let's go ahead and determine the geometry about each atom. Okay. So let's take a look here at the carbon number 1 here. And we see there's 4 bonds, 0 lone pairs, and of course 4 charge clouds, if you will. So this has got both a tetrahedral electron pair geometry and molecular geometry. Let's take a look at the oxygen here. So the oxygen, again, we have 4 charge clouds. There are 2 bonds, the 2 carbons, 2 bonds, and 2 lone pairs of electrons. So this has a tetrahedral electron pair geometry and a bent molecular shape. Then let's take a look at carbon number 2 here. Again, same as carbon 1. 4 bonds, 0 lone pairs, 4 charge clouds. So we have a tetrahedral electron pair geometry and tetrahedral molecular geometry. Let's look at carbon dioxide. So we draw the Lewis structure for carbon dioxide. So we have a carbon and a double bond to these 2 oxygens, and let's see, we have the 2 lone pairs on each oxygen. So we're looking at the central carbon atom, and we see that there are 2 bonds, and we count a double bond, a single bond, and triple bond as 1 bond. So we have 2 bonds. So the carbon is bonded to 2 oxygens. We have 0 lone pairs, and we have 2 charge clouds, which are the 2 bonds. So in this case here, what we have is a linear geometry. So both the electron pair geometry and the molecular shape are linear. We can do this molecule here. Again, I can draw the Lewis structure. We have this, and then the hydrogen. And this is the same thing. We're looking at the central carbon atom. We have 2 charge clouds, 0 lone pairs. So that's 2 bonds. The carbon's bonded to a nitrogen and a hydrogen. And what we have again is a linear electron pair geometry and a linear molecular shape. Let's take a look here at the nitrate ion. We did that before. And what we have is we have this species here. And we look at the nitrogen. There are 3 bonds, 3 charge clouds, and 0 lone pairs. So what we have here is a trigonal planar. And let's do one more. We'll do sulfur trioxide, and we'll draw the Lewis structure for this. Let's see, we have 24 valence electrons, and let's just go ahead and draw this. And let's get these electrons around the oxygens. Okay, so we see everything has an octet. Oh, we have to count the number of electrons. So we have 18, 20, 22, 24. So we need an octet on the sulfur. So let's go ahead and move a pair of electrons from the oxygen, and we'll form this double bond here. So now everything has an octet. And so we can draw resonance structures here, remember, but I'm not going to do that here. I'm just going to use this one structure to determine the molecular shape. So what we have is the central atom, the sulfur, 3 charge clouds, 3 bonds, 0 lone pairs, and again, we have a trigonal planar. Now, let's go back and talk a little bit about polarity. We already talked about polarity and bonds. So let's talk a little bit about polarity as far as some of these structures go. Let's look at carbon dioxide. We know that both carbon-oxygen bonds are polar. Okay, you can the electrons are being pulled in opposite directions. Okay, to the oxygens, and even though the bonds are polar, the molecule itself is non-polar. So when you have a linear shape, and when both atoms that are bonded to the central atom are identical, whether the bonds are polar or nonpolar, you will have a nonpolar molecule. If we look at this one here is linear, but the nitrogen is very electronegative. It's pulling the electrons towards itself. And so the electrons are going to spend more time about that nitrogen than the other atoms. So this is linear, and this is a polar molecule. So in general, when you have a linear molecule, a linear shape, if the atoms bonded to the central atom are not identical, you will have a polar molecule. And then let's take a look at this nitrate ion. We don't talk about nitrate ion or any other ion as being polar or nonpolar. Remember that when you have ions, okay, these are electrically charged particles, okay, and many ionic compounds do dissolve in water, which is a polar substance. So we don't talk about the polyatomic ions as being polar or nonpolar. Let's take a look at the trigonal planar sulfur trioxide, and remember each of these bonds points towards the corner of an equilateral triangle. Okay, so these bond angles are about 120 degrees. Okay, so what you have here is even though these bonds might be polar, okay, what you have here is a non-polar molecule. And that's basically because the electrons are distributed equally about those atoms. Okay, so it's non-polar. Again, you have this trigonal planar all of the atoms bonded to the central atom are identical. It's going to be nonpolar. If we were to change one of these atoms, then you're going to have a polar molecule. So symmetry really plays a lot in polarity. Here's our favorite molecule, methane. And we know that this is tetrahedral, both the electron pair geometry and the molecular shape. And the carbon-hydrogen bonds are nonpolar, and therefore this molecule is nonpolar. Now, what about this one? This one here, I have 4 polar bonds, and so all 4 bonds are polar here, but the molecule is nonpolar. Again, the electrons are distributed equally, okay, about these in these bonds. So in general, if you have a tetrahedral molecular shape, then if the atoms bonded to that central atom are all identical, your molecule is nonpolar. However, let's say I have something like this. I've got 3 polar bonds, but I have this other bond that is nonpolar. So this molecule here would be considered polar. Look at the symmetry. We have a tetrahedral geometry, molecular geometry, and notice that all 4 atoms are not identical. So there's going to be a polarity involved with this. For example, ammonia, we have this trigonal pyramidal molecular geometry. Okay, remember the electron pair is tetrahedral, but even though these bonds here are equivalent, we have this lone pair. All right, so the electron distribution is not the same throughout the molecule. This is a polar molecule. And now I think you can see water. You can see the same thing with water. Here we draw the Lewis structure for water. And we know the molecular shape is bent. Okay, so again, there's not an even distribution of the electrons. So this is a polar molecule. I hope this helps. If you have any questions, please contact me.